CSIS 2430 is filmed before a live studio audience.
Welcome to Karnaugh Maps. These are really cool tools here, okay? So we're gonna start baby steps because it's a little tricky at first to wrap your head around, especially if the way it's written up in the book, the Kenneth Rosen book. It's a little bit tricky. He does a little bit differently than is sort of traditional. So I want to make sure I show you how the book does it and how I'm going to be doing it. And you can pick which way works best for you, but let's just do it in baby steps here, okay? So first thing, making the map, all right? So what is this all about? This on the left-hand side is our truth table, right? It's just a function that has the output of 1, 0, 0, 1. That's it. And that function is determined by the x and y values, of course. Well, the thing on the left is a regular truth table. The thing on the right is what's called the Karnaugh map, but it's kind of like a truth table still. So the first step is to basically transfer the data from the truth table to the Karnaugh map, okay? And we'll talk about how these are labeled when we get to the bigger ones that are using more than two variables. But with just two variables, x and y, it's pretty straightforward. This is your x side, this is your y side, and then we're looking at 0 and 1, and then 0 and 1, okay? And it does need to be in the same order as, you know, if we go 0, 1, then it has to go 0, 1 here. Now you can go the other way. You can go 1, 0 as long as you go 1, 0 here, okay? And in fact, that's actually what the book does. They put the positive at the top and at the left. So we'll look at that in a few minutes. But for now, just know that we have to have these labeled like this, all right? We have to have the 0 and the 1 there, okay? Well, this is super easy. All we got to do now is look at this and transfer the values over there. Well, let's look at the first value. This is a 1 right here. What gives us a 1? Well, it's where x is 1 and y is 1. Okay, so x is 1, y is 1. That's this spot right here. Okay, so what do? We put a 1 there. Okay, we look at the other 1 right here, and we see that that's where they're both 0, which is that quadrant right there. Everything else, we just put a 0 in. All you have to do is fill in the 1s. Everything else is a 0. Okay? So you find where the 1s belong based on the values over here, and you're good to go. Just fill in the rest with 0s, and we're good. Okay? Now, this is the beginning. There's more to the Karnaugh map than just this, but first we need to wrap our heads around transferring the data. So, now you get to try it. Here's your truth table. Pause the video and see if you can fill it out in the Karnaugh map on the right. Okay, hopefully you got it, and here is the answer. The first one there is where x is 1 and y is 0, right? Which is this one right here. X is 1, y is 0. And the second spot is where they're both 0, which is that spot right there. Okay, now that we've got the idea of how to put it into the Karnaugh map, let's look at doing it if we don't have the truth table, because maybe we've just been given the function, or we just have the function written out. We figured out what the function is based on looking here, and we just have the formula. We don't need to worry about the truth table anymore. So let's take it here. We have this function, and the question then becomes, what values go where? Okay, well, just look at it this way. This is saying x, y, which is true, which is 1, 1. So that's where x is 1 and y is 1. Which goes over here. And then the next one is saying x is 0, right? X bar, and then y. So where x is 0 and y is 1, that goes right there. Okay, but you may be asking yourself, what's the point? Okay, what is the point? Well, the point is, now that we have a visual representation here in this Karnaugh map, we want to make circles. Okay, what are you talking about, Jeff? Circles? The idea is this. We want to group together as large of a group as we can and as few groups as we can that contain 1 or 2 or 4 or 8 or 16 or just counting up binarily, right? That many values. So in this particular case, it's so small, we actually can make a circle of 2, right? It's got 2 values in it. Now we could have also made a circle of just 2 separate circles that have 1 in it, right? Because 1 is allowed. But remember, the rule is, there's 2 rules. Rule number 1, as few circles as possible and as large of groups as possible, right? So that being the case, then we are looking for that. That is the largest group we have, and it's the fewest number of groups we can have. Well, what's the point of that? What does that do for us? Well, if you look at this, take a look here that in this particular circle here, just look at only the ones in the circle. And again, these are only ones. We're only circling ones. We're not circling zeros. We're circling all the ones here. And now what happens is we will always get a 1 regardless of the value of x. When x is 0, if y is 1, right? If y happens to be 1, x's value is irrelevant. If y is 1, we always get a 1, no matter what. Whether x is 0, whether x is 1. We always get a 1 if y is true. Okay? Well, what's that mean? Well, that literally means that this circuit reduces down to just y. That's it. The whole circuit reduces down to just y. Okay? Now we're going to see some bigger circuits that can reduce down. This is a pretty small circuit to be reducing. But we're going to look at some bigger ones in a few minutes. But I want to show you this basic idea here, right? So, and we can look at those laws that we looked at a minute ago, and we can actually prove this to ourselves. Now we're going to prove it mathematically and using a circuit diagram, but let's look at it mathematically first. If I take this equation right here, and then I factor out a y, I get that. And notice we got this little guy right here. Well, that's the unit property. With the unit property, this becomes this, and that becomes that. So mathematically, it does follow that this equation is the same as that, okay? But let's take a look at it in the circuit simulator. Okay, at the top here we have the first circuit, right? And the bottom we have the second circuit. And you can see there's a huge drastic difference here. And if you'll recall what we said when we looked at that Karnaugh map, that if y is 1, x's value doesn't matter. And you'll notice here, no matter what I do to x, this stays at 1, no matter what I do to x. If I turn off y, no matter what I do to x, it doesn't change. Y has all the power here, right? So this x is completely useless. So all we need is whatever y is. Well, if y is 0, the output's 0. And if y is 1, the output's 1, regardless of x's value. So that's just this simple little circuit right here, which isn't even really a circuit, it's just a line. If y is 0, then the output's 0. If y is 1, the output's 1. All right, let's check out another one here. Same idea, we have x, y bar, x bar, y. Well, where does x, y bar go? Just think of that as 1, 0, right? X is 1, y is 0. Okay, 1, 0. 1, 0 goes there. And then the next one is where x is 0 and y is 1, which is going to go there. So we end up with this. Okay? So that is moving the formula or the function into the Karnaugh map. The question now is, where are the circles? Well, remember the rules. You want the fewest number of circles and the largest size of circles. Well, part of the rule of the circling is they have to be adjacent but not diagonal, right? So this is not a valid circle, okay? If I had a 1 here, then this or this would be a valid circle. But in this particular case, there really is no useful circle. That's a valid circle. Those two circles individually are valid, but it doesn't change anything, right? If you just have a circle of each individual, then the reduced circuit will be what you started with. And in this case, there is no useful circle, and so there is no reduction. So if all of your circle groups only have one value in them, then there's no point. There's no reduction that's available. So let's remember what these rules are. Okay, first rule of Karnaugh maps. Circle groups of 1s in adjacent clusters of 1, 2, 4, 8, etc., right? Circle groups of 1s. You don't circle the zeros, you circle the 1s, and they have to be adjacent, as in left, right, top, or bottom, but not diagonal, okay? Next up, make the fewest number of circles, right? If you can make just one circle, then you're going to have a hugely reduced circuit for sure, okay? So the fewest number of circles. Make those circles as large as possible. They're circling the largest group that you can get, all right? And then lastly, if all the groups only contain one cell, then no reduction is possible. That's what we saw on the previous slide. Okay, so let's look at another one that I'm going to have you try this time, okay? So this time we've got 3 variables, right, in our function. So pause the video, and fill out the Karnaugh map and find the circles, all right? And see if you can reduce it based on the circles. If you get stuck, it's okay. We're going to walk through it in just a minute. All right, here we go. This is the place for all the ones. We take a look at the first one, x, y bar. That's just x is 1, y is 0, which is this one right here. The next one is x bar y. So x bar y, that goes right there. And then the last one is x bar y bar, where they're both 0 right there. Okay, so now the question is, where are the circles? Well, remember the rule. Make as few as you can and make the largest ones you can, right? So you may have fallen into the trap where you did something like this, or vice versa, like this. Well, but that sort of violates the rule of making the biggest circle, right? That's the fewest number we're going to get is 2, for sure. You can't do 4, or you can't do 1 circle because there's not a 1 here, right? But we can do this. Circle that, and circle that. Okay? So the circles can overlap. That's totally valid to do that. All right? So what's happening here is I wanted to have the fewest number of circles, which turns out 2 is the fewest in this case, but I want the circles to be as large as they possibly can. Well, even though this red circle exists, when I'm ready to do that blue circle, to make it as large as I can actually select that 0, 0 coordinate and that 0, 1 coordinate, because that's a binary number, right? 1, 2, 4, 8, and so forth. And so it's also the biggest one I can get. So that will give us our full reduction here. So if we look at the red portion of it, just the red portion, we see that whenever y is 0, x doesn't matter. When y is 0, doesn't matter x's value, will always get a 1. Okay, so the red is going to end up being just y bar, right? Look at the blue. Notice on the blue that whenever x is 0, y doesn't matter, right? In this particular spot, x is 0, y is 0. In this spot, x is 0 and y is 1, and you still get a 1 either way you look at it. So this will reduce down to the red, which is y bar, and the x, which is x bar, or the blue, right? Those two right there, that's it. That's the whole equation. It's reduced from this. And if you want to go through the Boolean identities to prove to yourself that that's accurate, you can do that as well to algebraically reduce it. And if it helps to sort of convert that back into propositional logic and try to reduce it that way, just to prove to yourself that it works, right? Okay, but again, the idea here is we look at each individual circle, right? So when I looked at the blue circle, what I'm looking for is things that are the same every time and things that change every time, right? So in the blue circle, x bar is always the case. It's always true that x bar is there. I'm just looking at the blue circle, okay? And when x bar is 0, I get a 1 no matter what value y is. Y has no bearing. It doesn't matter at all. So that's how I just say, well, all I need is that x bar because the y doesn't even matter. And then also, though, in this particular case, right here, I see that x doesn't matter because as long as y is 0, I'll get a 1 here. So if I have a situation where either x is 0 or y is 0, I will get a 1 no matter what. But that gives us a much more efficient circuit than this one right here, for sure. Now, as I mentioned earlier, the book does this a little bit differently, right? So let's kind of walk through that so we can get some clarity on that and make sure that it makes sense so that when you're reading the book, you're not too confused by it. So let's move that up over there out of the way. And really think about what's happening here. In that top left cell, what we're really saying is x bar, y bar, right? That's the top left cell, right? In fact, if you look at all the values, the next cell here, that's really just x bar, y. And this one down here is x, y bar, and then the next one over is x, y, okay? Well, we could have just as easily done it this way, where we have 1 and 0 this way rather than this way, right? Okay, so if that's the case, well, then this top coordinate becomes xy, and this becomes xy bar, and this becomes x bar y, and so forth, right? So this is a step in the right direction to understanding the book. The book gets a little bit weirder, though. Here's what it looks like in the book. And again, remember the book's using the bar instead of the actual little tick mark there, okay? But notice the book doesn't have this little weird thing that I've got going up here. right? That's just the way I like to do it because it makes it easier for my brain. But it's the same idea, right? But the book is doing, what he's done here is that he put x here and x bar here. Well, that's all that is, right? X being 1 and x is 0. That's x and x bar. Okay? So the next thing then, at the top, it's the same idea, right? This is y and y bar, right? Y is 1 and then that's y bar. 1 and 0. And then in the grid, you see these very values that I just pointed out right here, right? They match up exactly the same. So that's what's going on in the book. And I want to show you this because when we get to the bigger ones, we're going to look at how to do it with 3 variables and 4 variables in just a minute. So you need to understand the book to make sure that this is clicking, right? So between the book and knowing that you can reverse the order and that I prefer it this way, right? So hopefully that'll help with the next ones moving forward. And speaking of moving forward, we're now going to look at how to do this with 3 variables, okay? It's a little bit different, but it's still pretty straightforward, okay? So remember, this is what the book says for the 2 variables. Here's what it looks like for the 3 variables, right? Now don't panic, okay? Because in a minute, I'm going to show you how I do it with my little thing here, and I put an X here, and I put a YZ here, okay? So just imagine that. But this is the same thing. It's 1, 0. And remember, I'm going to be 0, 1 because I'm backwards or whatever, but that's 1, 1, right? Sorry about that. That's YZ, it's 1, 1. That's 1, 0. That's 0, 0. And that's 0, 1. Now, before I show you the next couple pieces that might hurt a little bit, I want to make sure we understand this next piece. This is critical. If you hear one thing today, please hear this. The order of these numbers matters, all right? Now, it doesn't matter if I start from the left to the right or the right to the left. That doesn't matter, but the specific relationship to each other matters hugely. Thing number 1, whatever order you go here, 1, 0, or 0, 1, you must start that same way at the top here. So because I started with 1 here, I will be starting with 1 here. And it will be all of the ones. Right? It'll be 1, 1, 1. Okay? Then the next here is we remove only 1. We toggle 1 bit basically, right? That takes us down to 1, 0. And then next we toggle another bit, which takes us down to 0, 0. And then next we toggle another bit that takes us to 0, 1. Okay? Now in a minute when I show you the way I do mine, you need to keep in mind this idea of toggling 1 bit at a time. That's critical to make sure that you do that. Otherwise, these maps won't even work. Okay? So make sure that you understand that. So you're either going to be starting with 0, 0 right here or 1, 1 right there. And that all depends on what you did over here. Okay? If you started with 0 over here on the left, then you're going to start with 0, 0 here, which is what I do. Okay? If I started with 1 on the left, which is what the book does, then you're going to have 1, 1 here. And then from there, you just toggle 1 bit at a time, okay? I'll show you that when I get to mine in just a moment. But let's look at one of the pieces that matters for this, which is this idea of a wraparound world, okay? So let me clear all this stuff out of here. All this means is this. If I have a 1 here and a 1 here and a 1 here and a 1 here, I can actually circle that as one group. That's one group. It's just like a wraparound circle, okay? The same thing holds true this way. Now, it's silly to do it right now, but in bigger Karnaugh maps, this can matter, right? In this case, why bother doing it wraparound? Because you can just do it that way, okay? But when you're wider like this can be very useful, okay? And later when we learn about 4 grid sizes here, right, it'll look something like this. Sorry about my poor art here. But then this kind of a thing can matter, okay? So we'll get to that when we get there, okay? But for now, just know that you can do this where there's a wraparound, all right? So let's take a look at a couple of examples here. Here's our first equation. We're going to put this in the Karnaugh map, and then we're going to circle the appropriate things and try to reduce it. Okay, so here's our first equation, right? This is the Karnaugh map that we're going to put it in. Now remember, I'm doing it the opposite way of the book, right? The book starts with 1 here and 0 there, even though they don't actually put 1s and 0s. They just put the full variables there. But I start with 0 here instead of 1, which means I must start with 0, 0 there. Okay, once I've done that, Then I'm just incrementing by 1 for the first one. I'm flipping one bit. I'm going from 0 to binary 1. But next up, you don't go to binary 2 right here. Sorry, let's try to do that again. You don't go to binary 2 there. Okay, you only flip one bit. Right? If I were to go to binary 2, I would have this here and then this here, and that's not good. Okay? So I flip one bit. I go from this bit to that bit flipping. And then once I'm at 1, 1, I flip the last bit. That gives me the 1, 0. Okay? So essentially, if that makes sense to your brain, great. If not, just think of this. You're going 0, 1, 3, 2. Okay? That's what you're doing. 0, 1, 3, 2. Okay, as far as binary goes. Right? But the way I think of it is I'm going 0 to 1, like you would normally count. Then, rather than going to the next number in the sequence, I flip the one bit to make it to where I'm not. In other words, if I went from 0, 1 to 1, 0, I had to flip this bit and that bit. I'm flipping 2 bits. Doing that flipping of 2 bits will make this Karnaugh map not work. Okay? So I think I beat that dead horse enough. Let's move on. Just don't forget it. Okay? All right. So look at this first one. We have X, Y, Z bar. Okay, well, X, that's the bottom row, right? That's all where X is positive. And then we have Y, or X is 1, I should say. Then we have Y, which is just these two, right? That's where Y is positive. And then Z bar right there. So that's that spot right there. All right? So there we go. The next is X, Y bar, Z bar, which is that spot. Then X bar, Y, Z, right there. And again, this is the X, and then YZ, right? YZ, 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 YZ. Okay? All right. Last one is all zeros, which is that spot there. That's it. That's all that's going to fit. Okay? So also note, you can make the table this way. I made the table the way it is on the left because I prefer that. But if you prefer the one on the right, this will also work. And so in this case, that's XY, that's XY, 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 and this is Z, Z. Okay? And we fill in the values the same way, right? So you end up with the table looking like that, okay? So now the circles, remember, fewest number of circles, biggest circles you can come up with. And I already see a wraparound here, right? So first of all, we have that circle on the left. That's a group of 2. Then we have this individual one. As you can see, there's no way to make it wrap around or be a part of another group. There's no way to add a second number in, a second value in there. So there's nothing we can do, okay? And then this one here, that is actually a wraparound case, right? So it's wrapping around, and so now we have 2 in that group. Also notice the significantly obvious lack of zeros here, okay? I'm just leaving them out for clarity, just so we can not have to think about them. We're just focusing on the ones. It's all that matters when you're doing a reduction anyway. Okay, but if I were to have done the map on the right, this is what the circles would have looked like. Something like that. All right, well, let's figure out what the equation will be. Okay, if we take a look here at the red, you can see that Y and Z, when they're 0, Y bar, Z bar, X doesn't matter. Whenever you have Y at 0 and Z at 0, if they're both at 0, hence we have Y and Z bar, Y bar and Z bar, then X doesn't matter. So that red circle reduces to that. Or it reduces to this, which is in the case of the yellow. Now it's a little harder to see because it's wrapping around, but notice it's always X. X is always 1. Okay? And then let's look at, these are the numbers, right? This is part of the yellow, this is part of the yellow. Well, notice that Y is 0 sometimes and 1 sometimes. So Y doesn't matter. As long as you have Z bar and X, you're good. So that's why the yellow reduces down to X, Z bar. All right, let's erase all this junk here. And then the last one, the green, well, it doesn't reduce at all. It's just X bar, Y, and Z, because every scenario, that's what you have, right? Because there's only one scenario. And if you look on the right-hand side, you would have gotten the same thing, right? If you look at the red, you'll see that in the red, that Z is always 0, and that Y is always 0, right? If you look in the yellow, you'll see that Z is always 0, and that X is always 1. And then lastly, if you look in the green, of course, it's always X bar, Y, and Z. Okay? So there, that's a 3-variable Karnaugh map, right? And here's what it looks like in the book, okay? And again, if you do that, you're going to get a similar equation. It may not be exactly the same. I'd have to look at this one and add it all together and see what we end up getting. But you may get the same equation, or you may get a slightly different one, but it will be logically the same, right? The results will be the same, okay? All right, next one. This one, we have a total of 5 minterms, which came out of a truth table somewhere, theoretically, and that's the function definition of f of x, y, z, and it's these minterms. So if we fill in all the data here, we get this first term is x, y bar, z. The next term is x, y bar, z bar. We get x bar, y, z, which is right there. We get x bar, y bar, z, right there. And then the last one is all of them are zeros, okay? So where are the circles? That is the question of the day. Let's take a look. Remember, the circle groups can be 1, 2, 4, 8, 16, and so forth. They need to be as large as you can find, and you need to make as few circles as you can find. Well, there's a big, fat, juicy one right there. 4. That's huge. All right, and then what's left is this 1. But again, remember, we want to make it as big as possible. Well, the biggest we can make it is actually 2, right there. So it's circling 2. So now if we look at our red equation, you can see that x changes, right? Sometimes pick any random one, like if I look at that one or that one, well, I have different x values each time. So x changes, so its value doesn't matter. Not only that, but z changes as well. So the only thing that's constant is it's not y. So look at it this way. If every single time I have a not y, or a y not, or a y bar, or whatever, x and z's value doesn't matter. I will always get a 1, or always get a true if y bar is true. So the red reduces to just y bar, that's it. Now look at the yellow. What's constant? X bar is always there, right? X bar is always there. And then also note that y changes. Y is sometimes 0, sometimes it's 1, right? Here it's 0, here it's 1. But z is always constant. So we got x bar and z, right? So it reduces to that. So this big old nasty formula here reduces down to that. Pretty crazy. And again, let's look at the one in the book. It's right here. Let me clear out some of my scribbles here. So in this case, the book's a little bit different because the book started with 1, 0, 1, 1, and so forth. It ends up looking slightly different, and they happen to have a wraparound right here. But you still ultimately get the same thing, right? You'll get a 2-component circuit, right? You'll get 2 AND gates and an OR gate, so a 3-component circuit. It may be different inputs, but it'll be a logically equivalent gate. All right, folks, now it is your turn. So pause the video. This is a big one. It's got 2, 4, 6, 8 minterms. Is that right? 1, 2, 3, 4, 5, 6, 7 minterms. So 7 minterms. Fill out the Karnaugh map, circle the appropriate groups, and try to reduce the circuit. No, don't try. Do it. There is no try. Only do or do not. All right, let's check it out. First up, let's put in the values, right? That's XYZ, XYZ bar, X, Y bar Z, X, Y bar Z bar, X bar YZ, X bar, Y bar Z, and all 3 bars, X bar, Y bar, Z bar. This is a big one, right? It's pretty big. So hopefully you found the good juicy circles, right? We got this one right here, that's 4. Okay, we also have this one, which is 4. And now there's this one little guy left right here, right? But remember the rule, you got to make it as big as you can. Well, it turns out you can make it huge. You can make it also 4. So the message I want to drive home here, overlapping is okay. Don't be afraid to overlap it, right? That's what you got to do. Remember, fewest number of circles, largest circles you can find, as long as the contents are 1, 2, 4, 8, 16, etc. Okay, let's reduce it down. Let's look at the green one first. And if you'll notice here, X is constant, right? I mean, there's no way around it. X is always 1 in this case. But look at Y, it changes from time to time. Like sometimes it's 0, but sometimes it's 1. So Y's value is irrelevant as long as X is 1. Okay, look at Z. Same thing. Sometimes Z is 0, sometimes Z is 1, right? So y and z's value is irrelevant in the event that x is a 1. And we are going to look at one more circuit to prove this when we get to the 4 variable K-maps. But I just want to make sure and remind you that I have proved it a couple of times that these reduced circuits actually do, or they are valid, right? So we've just reduced, though, this green one down to just X. That's it. All right, let's take a look at red here. Now, notice with red, this is interesting. Sometimes in the red circle, you have a 0x, and sometimes you have a 1x. So X doesn't matter, okay? Let's look at the Y. Well, Y is always 0 inside the red circle. So Y matters, as in Y bar matters. And then Z is different each time, right? So this just reduces down to Y bar. That's it. So the red is Y bar. And now let's take a look at the yellow one, okay? It's going to be very similar. It's just going to reduce down to one thing. As you can see, the X doesn't matter. It's 0 or 1. And you can see that Y doesn't matter either. The only thing that matters is just Z being 1. So this big old nasty circuit here reduces down to just X, Y bar, Z. Now, and remember, how did somebody get here, right? Was that person just dumb and couldn't figure out how to do it? No, not at all. They were probably given a big truth table that had all of these X, Y, and Z in it, and they had all these function outputs of 1s and 0s, and they were told, I need you to create a function that will give me these 1s and 0s, and that's the function they came up with. So you do that first, then you walk it through some algebra, or you walk it through a Karnaugh map, and you end up with this new function right here. And of course, here's the book version of it, right? And you'll notice it's kind of hard to see because all the lines are the same color, but they got this big 4 right here, and then they have this 4 right here, but then their other 4, it turns out it's a wraparound like this, right? Well, because our order was a little bit different, we ended up not having any wraparound. Now, it's not like the book magically has the highest number of wraparounds because it's always a wraparound if you do it the book way. No, it's just a coincidence that the ones we're using here, I'm getting lucky and having fewer wraparounds, that's all. Okay, you get to try another one. Here you go. This is a little bit smaller. It's only got 4 min terms. So ready? Fill out the Karnaugh map, circle the appropriate circles, reduce the circuit, or reduce the formula. Okay, here we go. First one, X, Y, Z bar. Next one is X, Y bar, Z bar. Next one, X bar, Y bar, Z. And all 3 negative, okay? So where are the circles? Well, there's one right there. There's another one right there. And that's it, okay? Now we could have done this and then done this. But there's some redundancy if we do that, because that's not the fewest number of circles. Remember the rule, fewest number of circles and the biggest ones you can make. Well, these are all the biggest ones we can make, but there's too many of them. There's 3 circles, right? And the book actually did it with 3 circles just to prove a point, right? And we'll look at that in a minute, okay? But here's the actual other set of circles. And here's what it reduces down to. Notice on the green that X is always 0, so X bar has to be there, and Y bar has to be there, but Z doesn't matter. No matter what X bar and Y bar, or excuse me, no matter what Z is, X bar and Y bar will always give you a 1, okay? Or you also have the case where X must be there because it's always X in the red circle, and we see that Y changes, but Z never does. It's always 0. So this equation becomes this, right? Now if we look at the book, this is kind of what I was talking about, but it's a little easier to see it since they don't have a wraparound in this case, and I did, right? So they have this circled and this circled, but they also circled this. Well, it turns out if you make a circuit out of this, you'll find out that this one right here, this YZ piece of it right here, doesn't even matter. You don't need that at all in your circuit, okay? So if you were to look at this piece, that would actually reduce to Y bar, Z bar, okay? Which is none of the ones that are in my formula, and that is not a necessary component. You won't need that. All you need are these 2 here. And if you just remember the rule, fewest number of circles with the largest amount of 1s in the circles, then you're golden. And doing this third one that's in the middle there that the book did is an unnecessary circle. Now, they didn't do it incorrectly. They were doing it to demonstrate a point, and it talks more about that in the book if you want to get into it. But it's just showing you that you don't have to circle every single thing. If you've gotten everything covered, then just do the fewest amount of circles. That's basically the point that we're making, right? Okay. How are we feeling about all this? I know I can't hear your answer, but I want you to stop and think. How do you feel? Do you feel okay? Because we're about to get into 4 variable K-maps, which are a little bit messier. All right, here we go. So first up, remember, this is how the book does it for a 2 variable K-map. This is how the book does it for a 3 variable K-map. And here is how they do it for a 4, right? Don't be scared.
This is it. Don't get scared now.
Again, this is the same thing as doing what I was doing here. And again, they're starting with 1, 1, which means you must start with 1, 1 here, and then 1, 0, and then you go to 0, 0 because you just flip that bit, right? 0, 0, and then you flip the bit again, and you get 0, 1, and you get the same thing up here, 1, 0, 0, 0, 0, 1. Okay, I'm just starting mine at 0, that's all. Okay, so that's the way the book does it. And again, you have wraparound, but you have some extra cool wraparound in this one. Okay, so you can have wraparound this way, right? You can have it this way, but you can also have it like this, for example, all 4, so that's a total of 8 in that one, or this way, okay? Again, just think of it as a cylinder, okay? And you can even have this as wraparound. That's one group, okay? That's one group, because think of it as wrapping both left to right and top to bottom, right? It's really weird. Talk about spatial thinking there, okay? But that's a cool way to go. And we're going to see a problem that does that in just a minute. Okay, so here we go. All right, don't panic. I know that's huge, right? It's a big, I think it's like 11 terms there. Here's what the K-map looks like. It's just a 4x4 grid. And again, I do mine. I have WX on the left, YZ on the right. By the way, you can put those, it doesn't have to be specifically that order, right? You can put the YZ on the bottom, the WX at the top. Doesn't matter. I just like going in the order of the alphabet. It just makes more sense, okay? And as long as you know which grid holds which value, you're good, okay? So again, I'm starting at 0 and 0, 0, right? And then I'm going to 0, 1. Then I flip this bit to get me 1 there. That's 1, 1. Then I flip the last bit and I get that, okay? And I do the exact same thing on the top. So this is W bar X bar. That's W bar X. That's WX. That's WX bar. And then at the top, right, you get the first one there. That's Y bar Z bar. Y bar Z, YZ, YZ bar. Okay? All right, groovy. Let's go take a look at how to fill this out. First one, right there. WXYZ. Okay? Then we get WXYZ bar, and so on down the line. The third term right there is going here, and so on. And we're just going to fill it in. I think you guys get the drift at this point. You don't need me to walk through every one. When all is said and done, this is what we get. This is our K-map. Okay, and again, the zeros would be in the other spots. Well, where are the circles? Okay, there's one there. There's another one there. Another one there. Another one there. And one there. They're all sort of these disparate, whatever that word is, separate, two groups. Not very, very good. Okay, but let's see what the function will be. Starting with the purple there. As you can see, W is always 1, but X changes, right? It goes between 1 and 0, right? So W right here, that's the W. It's 1 both times. The X changes. Sometimes it's 1, sometimes it's 0. So W is the case, but X is irrelevant. And notice that Y bar Z bar is always the case. So we need both of those. Okay? Look at the red one, and you'll see that it reduces down to WX bar Z. All right, the blue one here, it's WXY, right? Because Z is sometimes 1, sometimes 0. Let's go for, I believe green is next. Yep. Okay. And again, W bar and X bar are always true for the green. What changes is the Z, but Y is always the same as well, right? And then last, the yellow, it's going to be all 4 terms. Okay. You'll start to see a pattern here. The bigger your circle is, the more ones it has in it, the fewer terms are going to be in the product for that circle. Okay, so here is the final result. It's a lot smaller of a circuit for sure. Now I want to show you something interesting though. I did this K-map a different way, where I did the same exact values in the same exact spots, but I circled it differently. Okay, so notice there's still some similarities. I circled those two. This one's by itself, but instead of doing this, I did this. Okay, and doing that, this bottom set, I scooted those two, where basically that spot, right? That left me with a wraparound right here. Okay, so I have this wraparound on the green, and below it here is the formula that I would get. Now notice it's not the same formula. There are some similarities, right? The yellow one is the same, right? They're the same. And in fact, this one is the same, right? It's a different color, but it's the same. But the rest of these are not. These three components are not in there, and those three are not in there, okay? But it still works, and I can prove it to you, okay? So let's take a look at the circuit simulator. Okay, so take a look here. The top circuit is the first circuit I did, which was on the left of the PowerPoint right here on the left. And then the second circuit at the bottom is this one here on the right. Now, if these are the same circuits, then it doesn't matter which of these values I use in which circuit because they are logically identical. So the last two here, the W bar, X bar, Y, and then this last four-term one here, four variable one, is the same in both situations, right? So let's just do those real quick. And we'll see here that W bar, so W bar, I'm going to look at the top one here, X bar, Y gives me a 1. And if I do W bar, X bar, Y, gives me a 1 down here, okay? Let's do the last piece here. It's W bar, X, Y bar, Z. That gives me a 1 like it's supposed to. And then if I do the same thing down here, that also gives me a 1 like it's supposed to. So we can cross off those last two. They're identical in both circuits. But now look at this one, the middle term here, WXY, that doesn't even exist in this bottom circuit as the function we made. But if I do it, WXY in the top circuit, I get a 1. If I do WXY in the bottom circuit, I get a 1. And so on down the line. We can test every one of them. In fact, we have a WYZ at the first of this circuit here, which is not in this circuit. So let's do that. WYZ gives us a 1, and it gives us a 1 up there. Okay? Let's do this one, W, Y bar, Z bar. So W, Y bar, Z bar gives me a 1. And if I do that on the bottom, still get a 1. Let's do W, X bar, Z, W, X bar, Z. And they're the same in both circuits. So on down the line. Feel free to test it out yourself using proofs or the identities, or just trust the Karnaugh map, right? Okay, let's take a look at another example here. So again, bunch of variables here. Let's just fill in the map here, and these are the spots that they go in. If you fill in all the variables, you end up with this K-map right here. So where are the circles? Again, remember the rule. Biggest group we can find. Well, I can find a group of 4 right there. And what else do we have? There's 2 right there, right? And we have this group of 4 right here. That's pretty cool. So we got 3 groups total, red, green, and blue, and 2 of them have 4, which is going to be nice. It's going to be a really good reduced circuit. Okay, so let's take a look here at the red. If you look at red closely, you'll see that the only thing that's constant is Y bar, Z bar, right? W and X, like this whole big red circle, W and X are all over the place, right? They're 1s and 0s all over the place. But Y bar, Z bar are always the same. Okay, so that's good. If we take a look at the next one here, which is the blue one, you'll see that W and X bar are always the case, right? Because that's blue is in there, okay? But you'll notice here that Z is different sometimes, right? The only thing that's constant up there is the 1, which is the Y, okay? So that's W, X bar, Y, and then finally the green one, before I show it to you, right, let's see if we can walk through it. Now look at all the green spots. Here's a green particular place where we have 0 for W and 0 for X. But down here, W changes. So already W doesn't matter, right? But in all 4 of the green spots, X bar is true. So we need an X bar. Then look at the YZ. Well, if I look at the greens from this perspective, y bar, z bar is always true, except maybe not, because over here, y bar is no longer there. Y changed. So y doesn't matter. So when all is said and done, we end up with the only things that are constant every time is x bar and z bar. And again, look at that. You see that all of the greens, you have x bar right there, which I should be circling that one and this one, right? Okay. And then if you look at the top part with all of the greens, which is, we're looking in these spots here, z bar is constant, but y changes. So that's our final formula, nice and reduced. Here's what the book got. And notice they don't have a wraparound because theirs is a little bit different the way they did it, starting with different numbering. But it still is going to ultimately get the same equation, okay? Or the same circuit, I should say. Maybe even the same equation. Okay, your turn. Pause the video and fill out this big, nasty, huge K-map and circle everything that needs to be circled and reduce the circuit. Alrighty, let's fill it in. Here are the 11 terms. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. There we are. So your K-map should look something like that, hopefully. Where are the circles? This one's cool. We got a lot of big circles here. There's one, right? A group of 4 right there. And you may notice the group of 4 on the left edge and on the right edge. But we're going to come back to that in just a minute. Let's just look at the group of 2 here at the bottom. And then this big last group, it's actually not 2 groups of 4. It's one big group of 8. Huge group of 8. So this thing's going to really reduce down, okay? We have 11 terms at the moment. Let's see what it's going to end up being. Let's start with this big red thing. It just reduces down to z bar. That's it. Okay, and here's how you can quickly see. Right off the bat, it's clear that w and x don't matter. Because in the group, the circle here, they're all over the place, right? They're just sometimes 0, sometimes 1. There's no consistency, okay? Also, these pieces here we're looking at for the y and the z, right? And we see that y changes. Sometimes it's 0, sometimes it's 1. But z bar, it's always z bar. That's the only one that's consistent. So, we're left with z bar for the red. Pretty cool. All right, next up, the blue. Again, if we look here, blue, it's just a horizontal row here, and so the horizontal row variables are going to be consistent, right? Y bar and x, or y bar and x, right? They stay the same. But look at y and z, right? The blue circle involves all of those variables, all of those values, I should say. Sometimes you got a 0 for a y, sometimes you got a 1, sometimes z is 0, sometimes it's 1. So y and z don't matter as long as you have 0, 1 there with with w and x, then you'll always get a 1, regardless of what these values are. All right, last one there, green. And green doesn't reduce as much, but it still does reduce down a little bit. And we're down to wx bar, which is here, and then y, right? So if we look at the green, it's these pieces up here. Notice y is always 1, but z is sometimes 0, sometimes 1. So z's value doesn't matter. What it comes down to is if w is 1, x bar is true, or x is 0, and y is 1, then you will always get a 1 as your output. And of course, here's what the book gets, and it's, again, the same idea, but they didn't have a wraparound again, like we do. So their big fat juicy 8 is right there in the middle, okay? And then they have this one right here, and then they have a little side one there. All right, folks, I know this was a lot of stuff. The only way to get good at this, practice. Just keep practicing, keep trying it out. And sometimes, I know this is going to sound silly, but sometimes it's fun to just make up a random function and then try to reduce it in a Karnaugh map, right? When I was a kid, I first learned about long division. This is not a joke. I really did this. I went to the butcher store. We actually had a little local meat market that we went to. And I went to the butcher and I asked him for the longest piece of butcher paper he was willing to part with. And I made up my own long division problems on the butcher paper, just these huge, ginormous ones. Because I thought it was fun, because I was a dumb little nerd kid, I guess. Well, this, to me, still appeals to me in that same way. Just make up random functions, Boolean functions, and try to reduce them using either the identity rules from Boolean algebra or using a Karnaugh map, or using Quine-McCluskey, which we're not going to cover in this class, but it's in the book. Quine-McCluskey is weird, and it's a lot harder to wrap your head around, but once you get past 4 variables, a Karnaugh map is almost unbearable at that point. Anything bigger than 4 variables, you want to use the Quine-McCluskey method, but it's way more complicated. We're not going to get into it in this class. Anyway, I hope that gives you some good insight, though, into why this stuff matters. I love this journey from Aristotle to George Boole to Claude Shannon to modern day computers. It's just this cool thing, that something that had nothing to do with computers ever, and then suddenly now it does, and it's the foundation of the microcomputer. Without it, we would not have computers. Thank you, Aristotle. Thank you, George Boole. Thank you, Claude Shannon. So hopefully you can see the value of all this stuff, and it'll keep you chugging on. This is a fun and tricky class, and there's a lot of fun and exciting and difficult things coming. So hang in there, folks. Thanks for watching. We'll see you in the next one.